Okay, more of the trebuchet today. Before we do any more of the algebra and Lagrange equations and finally Hamiltonian equations for this fiendish piece of equipment, I'd like to go ahead and demonstrate one more time an actual flight of our miniature trebuchet right here, which we fired off at the beginning of this discussion last time. Right now I'm using the same projectile that I was using before, and it's just a washer, a heavy washer, but probably less than 1/10 the mass of the counterweight there. And we're going to try this shot, which I think is more probability of working than the last one. And everybody in the line of fire should duck, but it's probably not going to go any further than that table there that is there. So I'll ask the cameraman if he's ready to take it, and is it running? Okay, so lights, camera, and action. And that was a good shot. Perfect. Now let's show a bad one, which we'll talk about later on. And the story behind this is possibly apocryphal, but it was in a history text. And supposedly the last time a trebuchet really used to try to hurt somebody, besides a pumpkin, was in the 1600s when Montezuma was being attacked by the conquistadores, and they decided to lay siege to him in his castle, the Incas' hideaway, and they built a trebuchet out of all the materials that were available there, lots of wood in the forest, and they went to fire it, and I'll do the ceremony in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, fire. And that is one of the things that could happen. And in fact, if you build a trebuchet, that's something that you'll write. Now, what happened this time was the rope broke, and so I won't be able to re-demonstrate this doing what it really should have done. But Al tried it out just a few minutes ago, and the result was Montezuma's revenge. The projectile went straight up and came down and destroyed their long engineering feat of building a trebuchet in the jungle. So whether that's true or not, it's a good story, and also certainly shows how sensitive these things are to their various parameters. It is a very nonlinear device. So today we're going to continue a little bit of the stuff that we talked about last time in lecture 18 here. And we have in particular a couple of things that we need to get to. We built the Lagrangian force equation and the whole Lagrangian formulation in this particular thing. We'll go ahead and review a little bit of that. But I want to discuss the canonical momentum, the metric tensor's role in defining the canonical momentum, and then we'll go on and work out various forms of those equations, the particular Lagrange form and the Riemannian form, which is nothing more than whatever you have to do in order to get the second derivative on the left-hand side of the equation, and everything else that involves first derivatives or zeroth derivatives, that is, coordinates themselves, on the right-hand side of the equation. But the Riemann equation is something that we were going to learn about in order to have really the third, shall we say, nationality that is building mechanics in the 1700s and 1800s, Riemann being the 1800s. So we'll get started on that today, and then I will go ahead and on this screen here show you what we hope to get into is lecture 19. That's this one here. And the Hamiltonian equation for the trebuchet doesn't help doing the numerical study of this particularly well, although we haven't really pushed it, but you can see that formally it's more complicated. I've warned about this even with the polar coordinates, but the Hamilton's equations have their limitations, and as far as dealing with the algebraic formalism. And then, if we have time, but certainly in the lecture that follows this on Thursday, we're going to break from this formalism and just seat of the pants, build a very pretty algebraic approach to a special case of the trebuchet and analyze it and look at really what's going on in terms of its relationship or an analogy with, well, sports kinematics. I already told you that these sports that involve levers, such as tennis and golf, are what's left now that we don't have to work so hard anymore and we need recreational release. And the point of that really is to have that recreational release without having to go to see an orthopedic surgeon. And if you've ever looked at people on tennis courts, you've noticed they have bandages all over their joints very often. And that's because they are not following the physics of the trebuchet motion. And we wouldn't have a culture if that had happened to all the people who were building a culture with the axes and the hammers and the sai. They wouldn't have been able to play that game for more than a few years before they would have to go see an orthopedic surgeon, which didn't exist. So there's a lot to be learned from this little ordeal we're going through here to learn about mechanics at a complex level. So let's just quickly review what we did in lecture 18 so far. And we went through the geometry of this. There were a couple of different sketches that we've looked at. This is the one I think is probably the most efficient. You're just simply trying to find the x and the y coordinates of various points on the trebuchet, such as the end of the throwing beam that is of length little r. It goes from here to here, and then the weight is hanging on to that same lever with a distance of uppercase r. We have two Cartesian coordinates for that mass, and we're after Cartesian coordinates for this mass that's hanging on the point that has those coordinates. And the idea is to sum and difference these coordinates to get x and y equations, and there they are in terms of an origin that's right at the fulcrum of the trebuchet. That immediately leads to a velocity equation, and it is immediately also a differential equation. Here I've actually formed the partial derivatives that are necessary for that. Here are the two Jacobian and Cajobian sitting next to each other, one inverse or transpose of the other, and that becomes what we call the dynamic metric after we've loaded in any other masses besides the most important one is the trajectory. The one that's driving it is right there. It's one term. So this is where we look at the equation of motion in terms of just the part of the raw Jacobian that works. There it is for just this mass, extra term 1mr squared in there makes the complete Jacobian, and then the product of Jacobian and its transpose is the thing that we call the dynamic metric. Okay. Now the metric would have been larger if there were 4 degrees of freedom here. They're not because of the constraints of the levers involved. Later on we'll talk about what happens if you let the levers flex a little bit and all that sort of complicated engineering stuff. In any case, we have work sums that we produce from the Cartesian coordinates. There are 4 of them. So if we were just doing this with Cartesian coordinates, that's all we'd look at. But now we've narrowed it down to the 2 coordinates that matter for the constrained device. And here is a combination of d theta and d phi, written here with the force that is involved on the large mass and then the force that's involved on the small mass, Cartesian coordinates, little x and little y. Each of these terms is just an F equal ma. So this is the Newton's equation in Cartesian coordinates written out with an expansion that gives us eventually the equations that are Lagrangian Hamiltonian generalized curvilinear coordinates theta and phi of the main variables of this thing. And it better be true that they're independent. They are independent except at singularities of the Jacobian. So what we can do is imagine that the differentials are things that we can manipulate, and we can set all but one of them to 0. Here we set the phi to 0 and look at theta. The green coordinate goes with the big mass, and then look at the phi that goes with the small mass. And there's Newton's equations written one more time, F equal ma, but it's of course a sum of 4 terms on each side of the equation. This sum is equal to this sum. And at that point we do Lagrange trickery, a differential relation that lets us write each one of these, this one right here, and then that one and that one, rewrite those equations. And the idea is that we're eventually going to sum the whole thing. That's the thing that's really equal. Each one of these individual parts would only be an equation that was correct, say this one equal to that one, if there was no way for there to be coupling of energy out of the y coordinates of the small mass and the x and little x and big Y and big X coordinates. There was no coupling between those two. Then you could take each of these separate equations, but you can't. There's plenty of coupling between them. They're going to share activity, energy, momentum, all sorts of things. So this is the real idea here, is that we're going to be able to write this as a Lagrangian equation involving, in this case, the angle for the little mass projectile, in this case the Lagrange equation that involves theta. And we're going to add them up to get that. So here we are adding up all of the ones in this column and setting an equal to the sum of all of these in that column. And you see the way the sum is done here is to say that if I sum this mx dot squared plus my dot squared plus this little x dot squared plus this little y squared, sum all of that, that's what we call kinetic energy T, and it's in both of these equations. So there is the derivation of a Lagrange equation, just for the one of the generalized coordinates, but this is the form it has for all generalized coordinates, the two we have here and all others that we will consider whenever we're doing a Lagrangian thing. So these are the two equations of motion that we get totally in terms of the generalized curvilinear coordinates. Okay, that's called the Lagrange force equation, and you have to realize, and this is the thing that's a little bit different from the polar coordinate example we gave before. Here we have a sum of 4 Cartesian forces and partial derivatives going into make the thing we call F theta. The same thing for F phi. So these turn out to be torques. In this case, a torque with respect to the big mass. In this case, a torque with respect to whatever is happening to the throwing lever. And those are the, that's a different thing. And normally when we do a sum like this involving, in this case, covariant Cartesian coordinates over, in this case, 4, there would be 4 variables down here. That's not always the case. You have constraints that are throwing away 2 of the 4 variables, and we only keep them at the very beginning, and then from then on we deal with this fellow here, the covariant force, generalized force. So that's the equation written out, and then here we are actually expanding the thing out and looking at it. Now, one of the things I'd like to be able to do today is show some of the neat things that occur, sort of second guess these equations. The C, you know, if you sometimes you can very quickly check to see if you've gotten all the terms and plus and minus signs correct. We're actually writing out these guys right here in the force equation, F sub theta, and then we do the same thing with F sub phi. And one of the things that you notice is we have a minus sign here, so that's a force that you would call right-handed. And then there's a plus sign here due to the force that's associated with the throwing arm, that is throwing arm with the, let's see if I've got this right. I've got left-handed here and I've got right-handed here. So there's a right-handed torque on this one, that's the arrow indicating here, and there's a left-handed torque by gravity on the throwing arm, the way we've drawn it here. And one of the things you can say is, are there plus and minus sign errors here? And the answer is no, the beam has a minus coordinate already, so that you can second guess that one, that you've got that right. This one over here, this equation just involves the left-handed torque that's applied by gravity. And the minus sign indicates that it is left-handed for positive values of phi. Okay, now, I mentioned we want to look at that dynamic metric a little bit. This is the kinetic energy part of the thing, which has the dynamic metric coefficient. Not G mu nu, but in this case they use Greek G gamma to indicate that this is the thing that's going to have complicated expressions involving coordinates and masses. Okay? But no velocities in the actual metric matrix. Velocities are the things that are sitting outside being ready to make a quadratic form. So this is the quadratic form of kinetic energy in a generalized coordinate system, which for most mechanics just involves spatial quantities. But if you're doing relativity, particularly general relativity, this thing right here could be a full-blown relativistic metric. So we're using the same mathematical formalism when we tackle this in a Riemannian way as you use in general relativity, theory of gravity, and so forth. So this is our matrix with little m for the projectile, and one term involving the large m and large radius of the driving mass of the trebuchet. Okay, now when it comes time to calculate momentum, that's the partial derivative with respect to phi dot. So we're looking at a partial derivative here of the only part of this Lagrangian that has velocities. The part that would involve the gravity has no phi dots in it. Remember, that's one of the things that makes the Lagrangian equations valid, is to not have potentials that are functions of velocity. We'll get to those soon enough in later units that treat electromagnetic Lagrangians. This particular thing right here is just a linear function, if this was quadratic, because we've taken a derivative of the velocities, theta dot and phi dot, and so is this one. There's just a theta dot and phi dot term. That's the momentum, and you can see that momentum as the following. Basically what you do is you take the velocities, which are contravariant like component, that is, they are things that have their indices up, if I were to write them in the Q notation. So they're contravariants being turned into covariants. So all of that is happening now, even though the metric matrix here isn't just a geometrical one, it's got the masses displayed in it. So there is a relationship that is worth knowing. That is, once you have this dynamic metric, it's the thing that converts you from velocity to momentum, from contravariant velocity, generalized velocity, to covariant generalized momentum. And it should have an inverse practically everywhere, and that means that you can get the velocities in terms of momentum very relatively easily, in this case very easily. This idea of having a metric that lowers the indices of contras and makes them more peace-loving covariants, that's something we really need to prove in general. So here is one proof. The other proof that involves the matrices is just a couple of slides ahead. But this is where you get a little bit of experience using the sum rule for these indices that are repeated. And starting right here, we have an m and an m repeated, so I have to sum over that. An n and an n repeated, and sum over that. This is fairly small blue writing, so it might be a good idea to pull the focus of the camera up just a little bit to pick up this small stuff, and then pan down to this small stuff right here, where we're summing over here now, not m and m, but j and k. And the idea is that if I'm going to take a partial derivative with respect to velocity m, now here are indices that appear on different sides of the equation, so this is just a set of equations, one equation for each of the possible values of m, whereas this thing has no indices on this side, and there are two repeated indices on the other side, so that's a sum. And when I go to take the partial derivative with respect to m of this sum, I have to be careful. First of all, it's a differentiation of two things that have velocity dependence. Now, once again, this is something I don't want to ever see at this level of our thing, is a metric that has a velocity in actual matrix. So we'll skip that one. It cannot have any explicit dependence on velocity. Its job is to round up the quadratic terms that are sitting there. So I have one derivative for the first factor, q dot j, being differentiated with respect to the m. And then I have another one down there. Now, at this point, I have a partial derivative of q j with qm, both of them dotted. That means they're both velocities. And the understanding is that that is simply a delta function. That is, this is the variation of qj dot with respect to a particular q dot m, with all the other ones that are not equal to m being held constant. So that would simply be a derivative of x with respect to x, and that would be 1. But any other variable, m not equal to j, absolutely has to be 0, because that's the understanding we have for partial derivatives, is that when you're taking a derivative with respect to the velocity m, all the other ones are frozen. So the other ones include the j, and if it's frozen, it can't have a derivative, so this has to be 0. Remember that little story. Similarly for this one right here, you see, it's going to have a 0 unless k is equal to m, and then it will just be a 1, and I can drop it. So you add up those two. Now you have here a sum over k here, and you also have a sum over k there. Okay, but the k's only going to light up for a particular value m, okay, or in this case j equal to m, so I'm going to put an m in there, and I'm going to have gamma mk, and then this one's going to have the k, the second index of gamma equal to m. So this looks like I've got two terms, but I only have one because this guy is always symmetric. Metrics, just like the polar coordinate metric we looked at before, this one has better have the same number here as you do here. So mk is equal to km. And this one you see is summing over the second index, this is summing over the first, the j. That shouldn't be different, so I lose the half. And there's your answer. That's the proof of this in Riemann covariant notation. The covariant peak momentum being equal to the dynamic metric times q. Now, matrix proof is, we could just go directly to the way we wrote this in the original thing. If you do that, you get yourself into some funny notation here, okay, where I get a unit vector here, okay, a matrix here, and this thing sitting there, and then over here I've got the partial of these vectors, same thing, a unit vector. Add those guys all up and get a thing like that, and get 1/2. Symmetric matrix becomes that if they have symmetry. So, that's the matrix person's way of doing things as compared to the tensor person's way of doing this particular very simple proof. All right, so we now are going to get into the really ugly sort of stuff that is really behind the scenes here. Just think of all the forces that are acting to make this trebuchet work. Our little one, or else some monstrous 30-ton thing that sits as a defensive tool on top of some European castle. There's a constraint force here that's holding the thing onto the beam. There's a centrifugal force when it's actually moving. It's proportional to theta dot squared. So forth. There's a constraint force here that's just always along the lever, if it's particularly if the lever is a rope, and there's then a rope can only exert force along it. But with a throwing lever, there might be some constraint forces off a little bit there. There's a centrifugal force and a Coriolis force that are proportional respectively to products of various velocities. And then the one force that we do have to worry about is one coming from the outside, gravitational force. And there are two of those, and theirs are already built into our equations. But all of the other internal forces are canceling. They're all canceling with respect to each other. How this happens, eventually we're going to get a closer look at that. But right now, because we've derived these equations, we can say, isn't this wonderful? I don't have to worry about all of those other forces. They just don't arise at all in this equation. And furthermore, if it's an ideal situation where these can be written as potentials, particularly gravity, where you're just talking about a gradient of something that's proportional to a mass times gravity times the altitude, y-coordinate, you have an extra piece of luck, and that's when you can define a Lagrange function as t minus v and turn this more general equation into the specific equation that applies when we have an active, proper potential, only a function of coordinates, not a function of the velocities. Not yet, anyway. When we get to electromagnetism, we'll find a way to do that too. But here, we have restricted the potential only to functions of the coordinate variables. So, very easy set of equations to be remembered for each of the generalized coordinates, in this case the beam theta. You've got two equations here that involve the derivative of the Lagrangian. One is the p without a dot and the theta with a dot. The other one is the p with a dot and the theta without one. So that's, I'd say, mnemonic efficiency that is worth having. Not the way it's usually written, but it should be, as you can see. This is more considered. And of course, what we do is we just write this equal to some force, and then we can take the force, make it a potential, and put it into that form. Now that is certainly one that you could probably remember the rest of your life, even if you don't stay in physics. You can't forget it. It's very hard anyway. Okay, now force analysis. And this is where I warned before when we did this with just one set of polar coordinates. You now want to write an equation for the change in momentum, which is, in a sense, that has to be a generalized force that plays a role here. And you take the time derivative formally of the momentum. That is, you apply the metric to the velocities, and then take the derivative of that, total derivative of that with respect to time. So you must now not just look at explicit dependence, it doesn't matter. That's hidden in all of the variables that can move. So I say this is very easy to miss a term when you're doing this step. So I have to go through there, and if R, big R could flex, I'd have to have a derivative for that now. If little r, the beam that holds the lever, could flex, I'd have to have a derivative, a term for that. And finally, if the actual throwing lever, L, flexes and the R flexes, I've got to have two derivatives, two more terms just for that one right there. But we're lucky here. The only thing that can move in this term is this thing. The velocity obviously can accelerate. And so can that velocity, so we're going to need a term for that. And then we're going to need these two guys. They're definitely going to have non-zero total time derivatives as indicated by the dots that are showing up right here. So you have to go through and formally produce. Now this term, as I said, only has one that changes, so that's the acceleration term. And then for the theta. But there's also a phi dot right here. It immediately gets a dot on it. And I go on to take on the theta and the phi, so I get terms for each of those. So there is one momentum dot equation. Here's the other one. Okay? Now, these are going to be set equal to a generalized force. Now, it does have an extra, this is the thing that you have when you write the Lagrange equation in this form. You also have what we call fictitious force terms, Coriolis terms, or centrifugal terms in the polar example we studied before. But this is really what we have. So we have the Lagrange equation now written as P dot, well, minus partial of t with respect to theta. P dot, of course, is the time derivative of partial with respect to generalized velocity. We've written it this way now because we have formal expressions for it. And then we have whatever the external force is, and then we have this fictitious force. So we've got to do a partial derivative with respect to theta of that whole thing that expresses the kinetic energy right there. Okay, we've got to use the same kinetic energy down here for the other coordinate. Okay, well, there aren't very many things in this part that have a theta dependence. There is only a term for that, or a phi dependence, and again, this is the only term that has it. So there is the expression for P dot in terms of force and coordinates and velocity. Here's the phi part of the same thing. Okay, so what we can do is put these expressions for momentum in, and that will be our equation of motion in the Lagrangian form. Okay. Now, it's true that the gravity forces are just functions of coordinates, so we can stick those in there as well. So that's what's going on right here. I've now stuck P dot theta at the end of all of this stuff I had when I took the formal time derivative of the kinetic energy. So there's a reasonable set of equations of motion right here involving accelerations, both of them, okay, and velocities on both sides of the equation. There are velocity terms. But what's really remarkable, and you'll see this quite often, no cancellation, it simplifies. Now, I leave a mean sort of thought problem for you. Why'd that happen? What's going on here? Okay, I'm not going to say any more about it, but it's interesting to note this. Okay, so it gets a little simpler. Okay, there is our equations of motion right there that we write from.
Can you once again state your problem? What's the thought problem? Like, you want to know why those terms cancel each other? Like,
yeah,
physically what
I
they
get
mean?
rid of 4 terms here. Yeah. That's kind of a neat thing that's going on. A little bit of symmetry, sort of. Yeah. But you can look at it a couple of different ways. Yeah. Anyway, we're thankful, right? Any term you can get rid of. Oh boy, that's nice. Okay. And so it's a good idea to know when it happens. Okay, now between here and here, I've manipulated the equations a little bit, but actually putting the values of these forces in with their gravity coefficients. That's the gravity part right there. So that kind of sums it up right there, Lagrange equation force analysis that we're talking about. Now, given those guys, I would like to get an equation that just involves the double dot on one side of the equation. That's what I'm going to call the Riemann form, because that's really what the Riemann form can be identified with. So I can take this and put it back together again, you see. And who do we see right here when I do that? Okay, I mean, I see something weird here. I don't recognize that, but I do recognize that as my dynamic metric. Okay, that's cool. That's really what's going to make this thing pretty nice. So I'm going to be able to invert this, unless I'm at a singularity, and write an equation that gives me this guy in the clear. So this is basically what Lagrange will give you. That's the Lagrange equation to boil down as far as we take it here. But if you realize that the metric is part of the deal, and that's something Lagrange didn't have. He really didn't have the concept of the metric, our dynamic metric in particular, here. So I'm going to push all this stuff up on the thing here. There's the original guys, and here's the thing that we're dealing with right here. Okay, and you can see that I can apply the inverse of this matrix to both sides, namely to that side right there. So this becomes a Riemann equation once I use this. Now this is generally not a simple matrix, because you see an inverse of this matrix requires the determinant, the thing that finds where the singularities are. When this thing goes to 0 or infinity, you're at a singularity. We're at a singularity whenever theta is equal to phi. So whenever the trebuchet lever, the driving lever, and the throwing lever are in line or tucked in, those are the two singularities where theta is equal to phi. Okay, this will blow up. Okay, at that point. So that's a thing you have to look for when you're doing simulations like we've been doing on a computer. You have to realize, make sure you don't crash the computer every time you swing the thing by the lever, one lever by the other. In any case, I apply the inverse, and that means I get this inverse matrix here, and then I get these terms here, the gravity term, and then the dynamic centrifugal terms. Those are really centrifugal-like terms there. So that gives you a Riemann equation, and most Riemann equations are, you know, nice to look at, nice to program. This has sort of a super inertia function, so I just write it as IS, okay, and with ISIS, just the I super, okay, and then I multiply both sides of this thing by that, and I have you know, a set of equations that are pretty easy to deal with, namely just this metric. So that's the Riemann form right there. I double time derivative equals some set of functions involving velocities and coordinates, all piled up. So that is about as far as Lagrange goes, where it steps on the property, so to speak, of the Riemann world. And we'll be doing formal looks at the Riemann world later on. Now this is more like stuff in Unit 3, where we really do the Riemann equation in this full tensorial notion, and we'll get to that at some point here. But what I wanted to do now is go backwards a little bit and just see if we can second guess some of these terms here. And one way to do that is just say, okay, I'm not going to have any external forces on this thing. Okay, so I'll have an equation that just looks like that, equals double derivatives involving the coordinates. Okay, so wanted to let this not be 0, but let it be pi over 2 plus or minus. I'm going to take the minus here because I turned things fairly nice. I'm going to have the super inertia here without the of this. If I turn that into pi over 2, I get plus or minus 1. So here's an inertia term that involves the rotational inertia of the throwing arm, and then inertia of the whole beam, including its main driving mass, and then the little mass that's associated with the projectile is sitting on a lever, but nevertheless it makes this coefficient. So that's the super inertia when they're at 90 degrees, and that's what I've got drawn here. Okay. So the idea is to second guess Riemann results, and I'm going to try to do that. Figure out what the feed torque on mass m on the throwing leg due to centrifugal force, and remember these things are all moving here, times the moment arm. Okay, now the moment arm, L, this thing right here, okay, we're imagining a centrifugal force because I'm rotating. I'm just drawing that force out there like that, centrifugal force, m omega squared times the lever arm, which is a hypotenuse of a right triangle involving R, and the lever arm, throwing lever L. Okay, there, that hypotenuse is figuring into a centrifugal effect, particular state of motion. Now, when we say this, I mean, if you look at what the theta dot dot is for this fellow here, we've got this part and we've got this part. And the idea is to see those things showing up. In particular, phi dot dot's kind of interesting. Omega squared R over L is what the Riemann equation is getting. How do we get a thing like that? Okay, well, we say force times lever arm. There's a lever arm right there. L is equal to R over the square root of R squared. That is the hypotenuse. Just making a similar triangle there, right? I'm doing L is to little l, okay, as the R is to the hypotenuse. Okay, so that's just proportion there. But that then gives you an expression for the, particularly the L value, okay? Here's the L, and then over here, let's see if I've got that right. I've got, let's call phi dot dot let's see if that's making sense. Well, we're taking omega to be identified with the actual coordinates. So this is an R squared omega squared, and here's the radius squared that goes with that omega squared. Then there's L right there. And that then comes down after you've canceled everything, take the ml squared to give you phi dot equal omega squared R and L. So that's the hand-waving derivation of that. Okay? So you see the power of the Lagrangian method is that it's doing all of the bookkeeping for us to come up with this. If I didn't have that and I was super good at waving my hands and my head as well, I'd be able to come up with it here. But that's why I call it second guessing. Yeah.
ml squared is the moment of inertia.
ml squared, the moment of inertia, just associated
with that little mass. About that pivot.
But the moment of inertia for the whole thing, that's a whole nother story, and that's what the next part of this does. We would like to see if we can figure out what theta dot dot is. And it's a fairly complicated little thing here, okay? But this one, we've nailed it just with a little geometry.
So that isn't that the torque, Dr. Harter? FL, because F is the force that acts and L is that perpendicular distance.
Yeah, this is a torque.
Yeah.
Here, this is a torque equal to inertia times acceleration. Right? Does that make sense?
Yeah.
Okay. Now we got to do that with theta too. You see, and that's more complicated. It involves the whole damn thing, right? This one we can just worry about this little piece here. Okay, but still, you can see it's the power of this is shown. That's really the only point I'd like to make here, but it's a good one to do. Okay. So here we're trying to second guess this part right here. And you remember I was doing it at a special point, so really I haven't gotten all of the power that the Lagrange is giving me. Now this theta coordinate, I'm saying here, this is kind of neat. We're talking about centrifugal force pulling on that thing. And I say it may seem paradoxical that the theta coordinate for the main beam feels any torque at all. We're talking about centrifugal force. This thing is in motion, okay? And centrifugal force goes right through the fulcrum. How can there be any torque if you don't have any lever arm, okay? And we're talking about the whole thing now, so it shouldn't be worried. And I say, if the device is rigid, that would be a valid argument. It's not. You see, this is this line of action hits the fulcrum all right, but this is capable of moving. So as I say, it isn't rigid. The L-leg pivot, that's this thing right here, is frictionless and can only transmit a component ml omega squared of force along L. Okay? That's the only component of this force that's really going to mean anything here. And it's not zero the way we've gone. Okay? So it's this thing that's going to be causing that thing. But how? Wow, we've got a lot of pieces in there that make that happen, you see. Okay, so, you know, second guessing is hard for this thing. And here I'm just explaining that roughly with the geometry that I've got. Okay, this will cause a negative torque. Okay, this force right here, this centrifugal force, only this component is going to cause a left-handed a torque on this thing, and there's a minus sign, mRL omega squared on this big arm here. Now let's see if I can even figure out how I second guess that one. That was done by doing a force L, and these two cancel right here. I get an omega squared RL. Okay, so that makes sense, but then you have to say, okay, well, what about these guys right here? And right now we're locked into a situation where I would be talking about this R squared here and this R squared here being summed. That'd be the inertia that I'm playing with to rotate. Okay, so it reduces the theta angular momentum to exactly cancel the rate of increase of the phi momentum. That's really what we're saying right there. See, so that's the thing that checks with the Riemann equation at this particular hand waving sort of derivation. Okay. Now, you've got to realize what's going on here. For every bit of angular momentum that this thing increases, I've got to lower it to this one. So this is really the twirling skater analogy. Here's the skater, and there's the skater's arms, you see. And if the arms are pulled in, the skater will turn faster. Push the arms back out again, and you slow down. So that's the kind of dynamics that's associated with the trebuchet motion. I want to play on that later on with a very simplistic model of this sort of double lever
Dr. I just have one question.
kinematics. Yeah.
That L omega squared R is the centrifugal force, right? In this case, what you define.
This guy right here.
Yeah.
Yeah.
So my doubt.
Here's the F equal ma equation. There's the acceleration.
Yeah, that's true.
And this is what came out of force times lever arm.
Right. Yeah, that's true. So
effective lever arm.
That force is radially outward, right? That's what.
This guy here.
Yeah, that's what is enabling it to swirl around the pivot. So why do you still have a minus sign then? Like,
well, this is all left-handed. Yeah, anything that goes clockwise is minus.
Okay.
Right? Anything goes counterclockwise, that's our convention, right? And I started the coordinate system off for this thing looking negative, right? If I wanted to be real clean and not have minus signs, I would turn trebuchet around and have everything, throw this way. And then I wouldn't have as many minus signs. But it's good to have those minus signs because they make you think about it, whether you got it right. That's just my feeling about this. The other clean way may be better for you.
Also,
Actually, you should work it both ways if you have time.
So had your radial force been acting inward, then you would have a positive sign, right? Like if you should.
Yeah, as far as the radial stuff goes, we always have conventions: positive outward, negative in. Yeah, that convention is pretty standard, I think. Okay, let's see if there's anything else. I think that's it. We'll now go to the next lecture here, and that is, we've just done away with 18, now we're going to 19, and we'll see how we can what we could do with this one. One order of business is one more time deriving Hamilton's equation. So let's get that out of the way, and then we'll have time to play, I think, down in this region of the thing. So we really want to go once again to Hamilton's way of looking at things, given the Lagrangian development. So this is a repeat, but just with a more complicated device in a single particle in polar coordinates. And this is a device. I also didn't point out before, they're in Cohokie, Illinois, which is up just across the bridge from St. Louis, an enormous Indian empire, sort of Washington D.C. of the Central Plains and northeastern Indians existed at a place called Cahokia, and it's not as spectacular as the Aztec or Inca installations in Central America, but it is every bit as populated as far as people can tell. The reason, perhaps, that it's not archaeologically rich is the Mississippi River, which, as you know, floods. And so a lot of this stuff got washed away. But nevertheless, they discovered independently the atlatl, which is a trebuchet-like throwing device that lets you throw a spear with it. So I mentioned that as the other sort of weapon. When we come to discuss our sports analogy, I'll mention it again. But in any case, what we're talking about here is trying to make a Hamiltonian out of our Lagrangian. Okay? Now remember, the Lagrangian is t minus v. We have to prove that a Hamiltonian is t plus v, but we need to know a lot more than that in order to be making a Hamiltonian a useful piece of equipment. So here is the differential, total differential of the Lagrangian. Here, assuming that our, say, force potential is in fact explicitly a function of time. And I indicated this sort of meddlesome behavior of changing the rules of motion as the motion goes on, with a picture of Professor trying to change the class size with a little knob. So somebody's turning the knobs on the potential here, and if they are, I need an extra term. I can't just get by with that stuff. Now, when it comes to discussing Riemann equations, we won't be allowed to do this. That's one thing about the German method, that you cannot handle explicit time behavior. Guess how they do it? It's called relativity. Time becomes another generalized coordinate. That's pretty cool, right? But for these guys, the French and the Irish, this is the way out for taking explicit dependence into account in equations of motion. So, got to keep that guy in general. Now, we can just call L dot the total time derivative of L by just really dividing by the differential dt. So I turn this differential into a velocity. Okay, and then I have accelerations right there, d phi d dot and d theta dot. Rather than rewriting all of that, we simply are going to keep them, but put in Lagrange's definition of momentum. And we're heading toward a Hamiltonian, so obviously that's the change of variables that we need. So here, same thing we did before with polar coordinates r and phi. We're doing it with two angles of the trebuchet. Okay? So there's the p dot partial L respective theta for that beam coordinate, and there's the azimuthal, well, it's the azimuthal, the projectile relative to the well, not relative to the B, we're going to do that later, but relative with the z-axis that goes through the B point. Okay, so Lagrange equations are put in to the chain rule, and then we recognize by combining these two things that we have that famous action combination, momentum times velocity. In this case for theta, then momentum of phi and velocity of phi dot. Okay? So we have a total time derivative of these things gives these four terms right here. Then we have this weird thing we call the explicit time dependence. Okay, so that's the total derivative. Okay? Time derivative of L now being pulled over on this side of the equation, and then we've put the partial derivative of L on the other side. Okay, so the total time derivative, this combination of action subtract Lagrangian, is equal to this, and that's usually zero if we're okay, so we have a conservation law right here of something, and that's something you already know the answer to that. We're talking about the total time derivative of the Hamiltonian function. Okay? That's our definition of the Hamiltonian in terms of the Lagrangian. We're right there. Okay? Make sense? We've seen it before, but here it is in trebuchet language. Okay? All right. Now, we take this one step further. We start to look and see, what would our equations of motion look like. Remember that momentum is related to the velocity biometry, so that's going to help us out here, because that's really what we have to do in order to connect the two worlds, the Irish Hamiltonian world and the French Lagrangian world. And eventually they all get subsumed under the German Riemannian world. Neither of the Irish or the French would like that statement, but it happened anyway. Here we're talking about looking at the time derivative of one of the momenta, say this one, beam angle, maybe polar angle, if you will. I'm saying a partial derivative of h with respect to theta is what? Okay. Well, we're seeing here, if I can take it right, I can take the partial derivative of h here with respect to theta. That's a explicit dependence. Okay. And this is here assuming by Lagrangian functionality. These are the Lagrange equations right here. If I take p dot here, let's see if I can do this. Partial derivative of h, this is the h here, with respect to p dot. Nothing doing here, nothing doing here, nothing doing there. Let's see, that's right. So what I need is a partial derivative of h with respect to theta. Neither of these are going to give me anything. Those are independent variables from the coordinate theta. But this one right here, they're definitely a function of theta. Okay, so the partial derivative of L with respect to theta, okay, is the p dot. Okay, so this thing right here, that is that particular derivative of Hamiltonian, is minus the partial derivative of L with respect to theta, which is minus p dot. And that's one of Hamilton's equations. Okay, we'll do the same thing with p theta. Okay, here, looking at this equation, well, now I do get something from this equation without looking at the Lagrangian. I get a partial derivative of h with respect to p theta, okay, is just phi dot, okay, and then minus a partial derivative of L right here with respect to p theta, but that is assumed, remember, our no explicit momentum dependence of Lagrangian, right? So that's out of here. We've got another equation, Hamilton's equations, okay? That's the first Hamilton's equation. There's the second, right there, those two terms. And this right here is something we did in Unit 1, Chapter 12. Okay? There's another one right there, partial h with respect to theta dot. That gives you p theta, okay? Minus partial derivative of L with respect to theta dot. Well, that does exist, okay, and it's equal to that. So this one right here is 0. That's explicit independence of the velocities. H cannot be a function of velocities. Same thing for the phis. Okay, so those are Hamilton's equations. And I've got them listed here, okay, for theta, and then again for phi. And that's the whole story as far as the equation side of the Hamilton theory. Except for noting this again. That's bizarre. The total time derivative of h is minus the partial time derivative of L. So if L doesn't have explicit time dependence, we got a constant of motion right from the start. Okay. Now, looking at the expression in terms of these things, I'm going to go fairly quickly through this. It's something you really should study yourself just to get used to it. The Lagrangian function with GCC is that guy. This one, the Hamiltonian function, here being a function of momentum, okay, that's the definition of the Hamiltonian. And then the relation, the whole relation is a Poincare or Legendre. It's usually just called Legendre. They don't mention Poincare really enough in any of this. But that's the idea, is here's the theta dot, okay? Here's the phi dot, p phi dot, and p theta dot. Well, p theta, remember, has got the covariant metric relation. So I stick in just the first line of that. And then the p phi has got also a metric relation, so I stick in that second line right there, multiplying phi dot. So that is what it comes out to be plus v. Okay? So what I get is this stuff here minus a half of this stuff. Okay? Work all that out, and you get a thing that looks like this. And that's just a kinetic energy. There are both lines of our covariant metric relations sitting right there with a 1/2 in front of it. Okay? And that's what we call kinetic energy. This is correct numerically, but not formally. This one has the right numerical values, does not have the right derivatives, partial derivatives. Explicit dependence of the function h is not being shown here. It's trying to take over the explicit dependence of the Lagrangian, and it's not allowed to do that. That's verboten. Okay? The Hamiltonian must be in terms of momentum. So we go back and change all of this, and that's what makes the Hamiltonian a little bit formally inelegant. Because I now have to go and look at the inverse of this that gives me velocities in terms of this. And that was the thing that had the nasty super inertia underneath it for the trebuchet. So here's where we get informal hot water, so to speak. Because each one of these things is more complicated than just the simple things that sat inside this. We got the super inertia, the determinant of this thing in the basement of every term. Okay? Nevertheless, if you do that, then you do have a formally correct and numerically correct Hamiltonian for the trebuchet. And we're just going to take a quick look at that. We only have about 10 minutes left here. So, as I said, I'm going to go over this fairly quickly. In any case, there's the Hamiltonian. a little more complicated, right? Because of this darn thing. Okay? And this is why you don't see the Hamiltonian shown very much. You don't get that until you get into the more advanced parts of mechanics, which we'll just nibble at a little bit today. The coordinate equations, which we just derived, have a fairly simple relation involving the contravariant metric. Hamilton wants to use the contravariant metric because he's using momenta as the primary kinetic variable. Okay? So when we take these force equations, here's what we're going to get. That's not too different from what we got before. In fact, it's exactly the same as the Lagrange gave us. Okay? So far so good. But you go ahead and expand this thing out with the phi dot and the theta dot. Now it's looking a little bit hairy because now I've got to use those darn contravariant components that have the super inertia denominator. All right? And that's not necessarily so nice. Okay? So you can see that we're going to be getting these messy factors. Okay? I just wrote messy factor because I ran out of space there. But I really want you to see this lesson on so-called elegance of the Hamiltonian. It's very elegant formally, and we're going to make a little bit of use of that, but may not be algebraically computationally. Okay, now here's where it becomes powerful. We're just going to nibble at this a little bit, but it's really quite a remarkable, I think, the turn of events. This is where we're going to do a little bit of what we call contact transformations, but they're just, it's a really very simple one. I'm just going to do a change of coordinates where I'm going to replace my previous coordinates, theta and phi, at least I'm going to replace, well, in a sense I'll be replacing both of them with something new. These guys are lab absolute coordinates, okay? They were all measured off of verticals pointing at the stars. Good thing to do, you get less of a problem with rotating coordinate frames that have extra dependencies that you might not otherwise like. But here's a case where it would make sense to define a beam relative, that is beam normal relative azimuth. Okay, so there's a perpendicular going through the tip of the main beam, and I'm going to measure my azimuth off of that thing. And while I'm at it, I could just as well have measured my theta, but I'm not going to do that. The theta b is still vertical absolute, so we're going to keep that guy, but we're going to be referring to the normal, you see. So here's the old theta here that was referring to off of the horizon. This one's going to be referring off the vertical. Okay. So those are the new angles that I'm just throwing those out there. I really only mean this one. I put that one in there just to make it so we had two that were different. So I'm going to have a new set of velocities when I do this. And those new set of velocities have to transform by Jacobian to my old. This is lemma 1. Okay? And looking at my definitions here, it's pretty simple. Partial derivative of theta b with respect to theta is just 1. With respect to phi, there is no phi there. This is just a constant, so that's 0. And then the phi is the one that's got two terms. Okay, with respect to theta, it's minus 1. And with respect to phi, it's plus 1. Okay, and forget the constant again. All right, so there is I would say that probably the simplest, non-trivial, generalized contact, whatever, transformation that you see in advanced mechanics. Now, what can we do with this? Well, you'll see that what we can do is we can make a momentum of one of these things that is a constant of motion for a trebuchet that is ignoring gravity. So we're going to be ignoring gravity you say, what the heck kind of trebuchet you ever had that would not have gravity? I mean, it's driving the damn thing, right? Well, I'm thinking Chinese trebuchet, which didn't have the mass, it just had a lot of people pulling on it. And I'm imagining that that's the only thing we've got on the moon. The moon's practically no gravity, so, or if we're on a comet somewhere with virtually zero gravity, and we want to throw stuff around, here we go. This could be your ticket, all right? So I'm going to make an analogy of this with the superball by studying it. So basically, we're going to have a trebuchet that's in a gravity field, and somebody is going to jerk on it, and then it's going to do its thing. It's going to throw something. So that's what we're after here. Okay, now here's the inverse. Okay, very easy to take the inverse of that matrix. Jacobians usually are pretty easy in the inverse category calculation. Okay, so now we have theta equals theta b minus pi over 2 and phi equal b. That's the inverse of that. In this case, the equation is easily inverted either in derivative or regular form. Now, it is crucial, after you've done this, that you maintain this as an invariant. This is Poincaré's invariant. Okay, it's really invariant because it goes with quantum phase, right? Remember that? K dot R minus omega t, that's the what we're really talking about when we're talking about the differential action equal P dq minus h dt, that's kx minus omega t phase, okay? So you really have to obey this, certainly from the classical point of view, but remember that underneath all of this is phase invariance, which is really sacred for modern physics. Here is very ancient physics, but make the point again is that when I do a Poincaré sum, and this is reduced action, I'm leaving the time thing off, I better get the same thing that I get when I use these new guys here, okay? So when it comes to using this transformation on that, I better get that. So the idea is the P transform has to be the transpose inverse of the one for your coordinates, okay? So when it goes for getting the new beam orient, that's what the B stands for, coordinates, in terms of the original star fixed coordinates, now I'm getting the beam momentum in terms of the old star fixed momentum, okay? The matrix that I will use will have to be the transpose inverse, that is the inverse of this transposed, okay, which is this, and you can just look at it, it's right there. And then this thing right here, same thing, you see, it's got to be the transpose inverse for going the other way. Okay, so this is how you transform momentum back and forth, and this is the way you transform coordinate velocity back and forth. Okay, so that this thing can be remain invariant. That is, that you will get the same thing for this as you get from this. Okay, so that's something you really. This is the advanced side of mechanics. Really makes a big point of this. So the resulting momentum transform that goes with this is that. So you really should go through this whenever you do some sort of change of variables. Because the thing is that you can make changes of variables in which you include momentum in a coordinate transformation. You can mix momenta and coordinates. There's nothing that's going to stop you from doing that, as long as you keep this constant. Or I should say invariant. Okay, well here's our old friend, the Hamiltonian, with its nasty denominator. And of course the potential hasn't changed at all. It's all kinetic bookkeeping that's making this a complicated problem here. And what I'm going to do is I'm going to replace the old momenta. Okay? It's pretty easy for this, but it's a little extra thing has to be done for p theta. Okay, p theta is just going over essentially without any change at all. All it did was change the origin anyway, so that was okay. But here you have and I'm going to go ahead and write the thing all out here. This is, I think, the thing written in terms of the beam relative coordinates. I can go ahead and, if there was any gravity present, I would change that too. But we're going to turn the gravity off. Okay? So, assume zero gravity. Cross those guys off and just work with this thing. Alright? And this is kind of neat, because what you notice is that, and this was what drove this in the first place, is this zero gravity H, not the one with gravity. Obviously it is a function of theta, but this is not. This part right here is not a function of beam relative. So I've got a new kind of momentum that can be constant. Okay, I didn't have that before. This time, now I do. And of course, H is not a function of T, so that's a constant too. So I've got two constants here. We can solve this problem in closed form fairly nicely. So I go ahead and write this thing out with this thing replacing PB, this guy right here being replaced by that new constant. There's another one over here, okay? And so it's just a matter of algebraic fiddling with this to make it work. So I'm going to divide through by ml squared this thing here that I've gotten, which is yeah, I think that's just the h and these things are as a constant here. Now let's see if I'm missing a little bit of something here. Where did that 2L? I'll go ahead and expand this thing right here, okay? And I've got, let's see. If I set that equal to a constant, there's the E right there. Let's see if I got that right. I think that's right, yeah. Anyway, you come down with a quadratic equation for the momentum, beam relative momentum here of phi. Okay, this is a guy that involves the throwing. We've taken care of the replace the theta with a theta b, which has a constant momentum, and that's this lambda. So we end up with a thing like this, where we're just going to call, I'm defining an I here as the sum of the inertia for the beam and the, I should say the large mass R, and then the throwing part of the main beam inertias, okay? And then I get another constant right here after I divide through by that ml. So we end up with this throwing momentum as a function of beam relative angle by simply solving this quadratic equation. So that's the result of that, okay, just using quadratic solutions, plus or minus. Now, I'm going to make some other simplifications so that we can make the analogy with a super ball, the other throwing mechanism that we're basing this course on. Here, the total kinetic energy we had before was this, with no gravity. And the momenta that we had before, the star-fixed momenta, was all of that. Now we transform that to beam relative coordinates and momenta. Okay, replacing the coordinates, replacing them with those guys. And we also have that connection right there. So I'm going to get here 2E, and then this stuff right here. Let's see if that's all there. I think so. Now at some point I'm going to pick the angles nicely. I'm also going to pick the levers equal. R and L, I'm going to make them equal. So we're going to use Siege of Kenilworth trebuchet at this point. And with equal arms. Makes the algebra a lot easier. So I get a relation involving conserved E, which is this, and it conserved that funny momentum that goes with the beam relative fellow right there is a constant of motion. So those are our two conserved quantities, very simple for R equal to L. So we're going to play with that, see what it is. Case of equal arms, easier algebra. And then we're going to look at this conservation, these two conservation laws, for a couple of cases. Starting point, this is the siege of Kenilworth all folded up and ready to throw. Then it starts throwing, gets out here to a point where you have, you would release, or you're actually putting in the most energy at this point, most transfer of energy, power is going into the projectile at that point. And then an optimum release, and you go past this, it's going to slow down. So the job here is to get the most energy into this thing. And we're watching the thing from a beam. The idea is the beam is turning. This is happening as the beam turns. I put the beams always horizontal so I just draw the relative position of the projectile. Okay. Start at 9 o'clock with this is minus 90. Theta B minus 90. Okay. So I'm going to end up with sine of minus 90. That's minus 1. So I'm not going to have this term at all for lambda. Okay. Just have this term. And then right here I've got a minus 2 product. So what I've got there is, besides this term, is mr squared times the difference of the angle associated with minus pi over 2. Okay, whatever velocity those phi angles have. And we're going to set theta equal minus pi over 2 equal to omega equal to, this is initially, you see, equal to this thing. So these two are going to be starting out together and then they're going to separate. So these are the initial conditions for this throw. Okay? You've got to realize how much screwing around I had to do to make the trebuchet actually give me an analytic result using Hamilton and Lagrange. Okay? So this is, you know, this is classical mechanics at its worst or best, depending on your your psychological take on it all.
You said that it's Hamilton's equation, solving Hamilton's equation would be computationally more challenging.
Well, you saw that it just sort of ends at a dead end with those nasty denominator expressions. Okay, so as far as formula goes, you better have Mathematica and know how to use it if you're going to play with the algebra. Okay, but it has the ability to show symmetry better than the Lagrangian does. At least the way the Lagrangian is done. I think Lagrangian can be improved so that it would do that too. But you'd just be using Hamiltonian techniques to do that. So right here what we're doing is we're saying, ah, wonderful, I got a conservation in addition to energy. Right? You know, Hamiltonian is energy, so it takes care of that automatically, right? But the momentum, I got another momentum that's constant. Once I've done that with 2 degrees of freedom, I've got an algebraic problem instead of differential equation solved. So that's what's going on here. Now we're going to move to the 6 o'clock thing. This thing is unfolding now, okay? And we've got theta b equals 0, okay? So I lose that term right there and just get a sum of squares. And I put in that value for this thing, and then our new constant, okay, with sine equal to 0, that's going to give me mr squared sum of just the angle velocities. This one's the angular velocity squared. Okay, so that's 6 o'clock, and then finally we're going to throw this thing. It's going to be released at this point. If this is an optimal release point, we're assuming that, and I think it's a reasonable assumption, okay? By this time, the beam R, with its big mass, has been slowed, and the throwing arm is, really whipping, okay? It's throwing. It's going to release this thing at its best, okay? And that's what we're trying to figure out. Okay, well, these are simple equations, but the algebra isn't that trivial, Okay? Basically what you're looking at is a phi minus theta squared here. You're looking at the sum of squares here. And you're looking again at a sum of squares there. So the idea is to play with those terms. These two guys here can be written that way, and then I can play with, see, I've got omega squares in this term, and I've only got omega in this momentum term. Okay, so I can use that to get an expression of the omega and angular velocity of the beam at pi over 2 in terms of the sum of those two angles. Okay, and then write the azimuthal angle associated with the pi over 2 expression that we had up here. This is minus pi over 2, this is 0, and there's plus pi over 2 that we're working on. Okay, so there's a relationship between theta dot and phi dot that we can then plug in to get that. And then I'm going to solve for that. Right there, the beam velocity eventually. There it is. Okay? That's an expression that's very analogous to the super ball throw things. If you look at what it is, a large M case for this, if I make M really large, then I just have 1 over 1, and I have phi dot here equal to omega plus 2 omega, that's 3 omega. Okay? So what this is telling me is for large M, really large, compared to sort of like our thing here, so that's got design problems that don't allow this to really happen. What I'm getting is that I'm going to be throwing this thing out there. The azimuthal velocity is 3 times the initial omega that I kicked this thing at. And then optimum, this is cool. The optimum case is when I have mr squared equal to 4 big R squared, 4 equal to 4 times the m, you know, little r squared. Okay. So that's something that's going to tell me about what my mass ratio and ratio of arms should be. Okay. And when I do that, I get a final velocity, not of 3, which, like the Super Bowl, remember, was the best you could do with a tiny little dust particle on top of a big mass, right? You get 3 times the velocity, right? And then when you optimize it, so you killed the beam completely and put it all in the thing, you got twice the velocity, right? In the Super Bowl problem. The Super Bowl problem, a lot easier than this, right? But it comes out the same. I thought that was cool. Otherwise, I wouldn't even show this to you. But the fact that it has an analogy with a really simple problem is, I think, really cool. Okay? So there's the analogy, remember. We could go 3 times if we made it really small, but if we killed it, we went to 2. Okay? Okay. That's all, folks, for the most difficult part of this course, I think, is this handling of the advanced Hamiltonian expressions. And now I'll show you an easy way to think about that problem next time, as we go back and look again at some things that have to do with the kinematics that build our culture and addict us to liver sports. Okay.